going to hear about causal gradient boosting.
Yep, I hope everyone can hear me well together. Okay, so we're going to change gears quite drastically compared to the previous paper. And the focus of this paper is going to be endogeneity. And endogeneity is one of the most common statistical issues that applied economic researchers face in their research. And that's why econometric literature has a long history of dealing with endogeneity using observational data. And it has been especially successful in estimating parametric models. And the seminal examples are the linear two-stage least squares estimator and a more general GMM estimator that allows us to estimate the wide variety of nonlinear models. But as any other parametric method, these methods suffer from the same problem. If the functional assumption isn't correctly specified, right, we will get the misspecification bias, and our estimates are not going to be that great. But and especially when we talk about nonlinear models, we have to be very careful about what instruments we use, because if we use weak instruments, we're going to be screwed. All the asymptotics go awry. So we want to make sure that we use strong instruments that actually explain all the relevant nonlinearities in the data that can help us identify and estimate the structural function. Of course, if we want to be more flexible and not worry about the misspecification issues, we can resort to non-parametric methods. There are series estimators like Nguyen, Powell, Blundell, Chen, and Christensen. There are kernel estimators like, for example, Hall and Horowitz. But all of them suffer greatly from the curse of dimensionality, and they only work with a handful of inputs. So the natural question that arises in this situation is, why don't we use the flexibility of machine learning methods? And the short answer is, we simply can't. We can't just take an off-the-shelf machine learning algorithm and apply it to an endogenous scenario and actually expect it to perform well. Right, so in this simple example, we see that these green dots are basically data points, and the true structural function is this orange line. So if we use a standard neural network to estimate such a model, we'll get this blue line, which obviously does not capture the underlying structural function. What it does instead, it just feeds the data. But that's what we should expect from the machine learning algorithm. It just feeds the conditional expectation based on the assumption that the error term is either independent or at least exogenous with respect to the features that you use. Right, so in this paper, what we want to do, we want to maintain this flexibility of machine learning methods and combine it with the instrumental variable analysis. And we do it by using the insights from the boosting literature and taking an algorithmic approach to function approximation under endogeneity. And in order to do that, we want to answer three major questions. The first one is being, how do we learn basis functions under endogeneity? And I will be very explicit what I mean by basis functions later on. The second question is, how do we learn the instrument structure? As I've said before, we want to make sure that we use strong instruments that explain the relevant nonlinearities in the data. And the last question, but not the least, is, of course, we want this algorithm to perform well, so we're really curious how it does perform. And spoiler alert, it performed pretty well. And I will show you some of the simulations at the end. So before I talk about our algorithm, let me spend the next couple of slides talking about boosting so that everyone is on the same page and everyone understands how it works. Okay? So boosting basically is a way to fit additive basis functions models of this following form. Right? And unlike the standard basis function model, these basis functions phi are basically simple algorithms, which are called weak learners or Bayes learners. Right? Asymptotically, it doesn't matter which algorithm you use, but in finite samples, of course, it matters. Right? And the rule of thumb is to use an algorithm which is simple enough so that the variance is low, but it can have high bias. Right? So the most used examples are the regression stumps, 1 or 2 layered neural networks, and the linear regression. And then we basically do the same thing as with any other algorithm. We just minimize the empirical risk based on some loss function. So for simplicity, we're just going to focus on the squared loss. And since we're only interested in the regression, not the classification problem, it's more than enough for us. So we're going to be basically living in this L2 boosting paradigm. But unlike the standard least squares approach, for example, we do not learn all the parameters simultaneously. It would be a very daunting task. Instead, what we do, we learn one basis function at a time. So under the squared loss, this problem of learning a single basis function becomes pretty simple. Right? So as we can see in the slide, everything boils down to fitting the weak learner to the residuals from the previous step estimation. Right? So at each iteration, we're going to fit the residuals and get the parameters alpha hat and theta hat. And then we will update our current estimate, fm-1, by adding the basis function along with the weight on it. And then we repeat this procedure capital M times, where capital M is basically the tuning parameter. Right? Fortunately, boosting is known to be quite resistant to overfitting, so we can always have many iterations, and we can just run it for a long time, hoping that our results are going to be good. But of course, in practice, you have to kind of think about computational time, right? So usually people will do cross-validation with early stopping. All right. Excuse me, just gonna. So the main question is how to accommodate endogeneity into this algorithm. Right? So we have this simple structural equation here. We have the vector of instrument z. And of course, we're going to use the exogeneity condition, which states that the vector of instruments is exogenous with respect to the structural error term to perform our estimation. So this exogeneity condition basically tells us that any functional transformation of the vector of instrument z can be used as an instrument. Right? But in order to get precise estimates, we want to use strong instruments. So the estimates of our basis function, they depend on the IV structure that we're going to use. But at the same time, in order to construct these strong instruments, we need to get some idea of how the basis function looks like. Right? We need to understand what we need to fit it to. Right? So we have the dependence of the instrument structure on the form of the basis functions. So we have this iterative interdependence in the algorithm. And fortunately, boosting is iterative by its nature, so we can easily incorporate this interdependence of the parameters into the boosting algorithm. And the key here is that we can use the basis function learned at step m-1 as a proxy and basically construct instruments for step m. So more details to follow. OK, so the only thing that is going to change compared to the standard L2 boosting is basically how we estimate our parameters at step m. So we just begin by taking the conditional expectation with respect to the instruments. And unlike the standard boosting, we're going to be fitting not the weak learner directly to the residuals. We're going to be fitting the conditional expectation of the weak learner given the vector of instruments. And the simplest way to estimate this conditional expectation is just to project the weak learner on the span of instruments. And here exactly the question of instrument construction kicks in. Right? So we need to span on strong instruments. Right? And in order to construct those, we're going to resort to the cross-learner idea of Gandhi et al. 2019. So basically what we're going to do, we're going to assume that we have a class of IV functions, H, which is parameterized by the parameter vector eta. And since IV construction is a mere prediction problem, we just need to find such a parameterization, eta hat, that fits the instrument vector well to the basis function. And to do so, we can use various off-the-shelf machine learning algorithms. We can use lasso, ridge, elastic nets, neural nets, whatever you want. So once we incorporate this step into the boosting algorithm, we'll get our boost IV algorithm. So the mechanics are the same. Instead, with the only thing is that we're going to be projecting on the learned IV transformation H. So that's kind of enters our projection matrix here. And then we'll be learning basically our basis function parameters conditional on the parameter vector theta hat. So we have this dependence between two sets of parameters, alpha and theta and eta, right? So we can use the basis function from step m-1 to learn the IV transformation. And then given the IV transformation parameters, we will learn new parameters for the basis function. So that's how it's going to work. And all looks good except for one tiny detail. And there is a small issue coming from the fact that both instruments and basis functions are learned using the same data. Right? And the issue actually comes from the fact that we use regularized estimators to pin down the IV transformation. So these parameters will suffer from the regularization bias. And since we use those parameters to estimate the basis functions in the second stage of our algorithm, this regularization bias will contaminate the basis function parameters and bias them. In order to avoid that, we can resort to cross-fitting and basically use different data slices to learn these sets of parameters independently of each other. So intuitively, how it works is like this. So we're going to partition our data set into k-folds of approximately the same size. And for each fold k at iteration m, we're going to use the data outside of the fold, this like dc, to learn the IV transformation. And then we're going to use the data inside the fold, dk, to learn the basis function parameters. And then for each and every fold, we will make our updates in the standard fashion. And the final estimator is going to be the average across these folds. So we achieve two things by doing that. First of all, we get rid of this regularization bias propagation. And second of all, since we use all the data to estimate both sets of parameters, we do not sacrifice efficiency, which is really important. OK, I think I'm even like running ahead of time, but OK, we can talk more about the results then. OK, we run a lot of simulations. I'm just going to show you one univariate design here, just because I have a cool picture, which I will show you in the next slide. But we also have multivariate designs and even some more economically driven applications that we'll talk a little bit more at the end of the talk. So here is a simple design with an observed confounding. So we have the structural function f. Then we have the composite error term consisting of some random variation, random shock like delta, and the confounder E. And this is the parameter rho, which measures basically the strength of endogeneity or confounding effects. And then we assume that we have like two instruments, and then the reduced form equation looks like this. And then we have four choices of the structural function. We have the absolute value function, we have the sine function, this like atrocity I just labeled as log, and then the step function. So I compare our results with a bunch of algorithms. We're not the first people who came up with like using some machine learning techniques under endogeneity. There are a couple papers out there. So besides the standard series and PV estimators that we have here, we have the kernel IV regression. And in my opinion, it's a very powerful algorithm. And then we have the deep IV paper, and you might have heard about that. And we also have the deep GMM paper. There is also a paper which is called dual IV, but for some reason their code doesn't work that well, so we didn't include it here. So anyway, so this table shows us out of sample MSE, right? And the first thing to notice is that NPIV doesn't perform that bad, right? I mean, and it's expected because it's a univariate design, so it should perform fine. Yeah, more than enough. Yeah. But the striking thing is that deep IV and deep GMM, they don't perform that well. So their MSEs are quite high compared to MPIV. And the main reason for that is that their variance is pretty big, because the default neural network architecture that these estimators have in their like open source codes are too complex, so that they drive up the variance. So in multivariate simulations, we see that they perform much better. So I guess that's kind of one of the main reasons. And we will also see that their bias is actually under control, so it's all coming from the variance term. And the final thing is that KAV and Boost AV, they perform pretty much the same. They have very small MSEs compared to other estimators. And we're happy with this result because with my experience, judging from my experience with the kernel IV regression, their setup is very, very powerful. And since we get results close to them, and in some designs we beat them, we're pretty happy that we can achieve that level of performance. So the cool picture that I wanted to show you is actually this. So here, the black line represents the true function. And the orange lines, they represent the average fit across simulation. So basically, this panel is very representative about the bias of the estimates in the simulations. So what we can see, NPIV is pretty biased, right? And as I told you before, deep IV and deep GMM, they perform much better in terms of the bias term. So like there were worse performance is mostly driven by the variance term. And we can see that the kernel IV regression and the Boost IV, our algorithm, they have very small bias and small variance, so they perform like better in both directions, which is pretty important. Okay, so I can spend more time on final remarks then, since I have a couple minutes left. So we do show consistency of Boost IV under mild conditions. And the only thing that we don't show, we cannot derive, we're not still able to derive the convergence rate because it's very tricky. Because showing that the algorithm is consistent is not that complicated, because there is like a very well-known paper in the literature by Zheng and Yu, which kind of provides a very general framework for boosting algorithms. And we just show that we can actually fit our algorithm to their framework, so the consistency follows kind of straight away. But deriving the convergence rate is much trickier, especially that we have this instrument construction step, and we need to take care of that as well. we also consider a couple extensions to our algorithm. The first one being, we talk about how to construct optimal IVs in the sense of Chamberlain, meaning that they deliver the smallest asymptotic variance. And also, we talk about the post-processing step. That's actually a very interesting thing. So the boosting algorithm, it's one of its kind of remarkable features is that after we have learned the basis function, when we move to the next stage, we don't go back and we do not re-estimate the parameters. We do not re-estimate the weight of the basis functions. We just keep everything the same. And Friedman and Popescu in their 2003 paper basically argued that for ensemble methods, it might be a good idea to go back after we have accumulated our predictions and re-estimate the weights, using whatever algorithm we want, like the least squares, the ridge, or like a neural network, whatever. And we also do that, and we can observe that in some cases the empirical performance is really, really great, but in some other cases it's worse than the baseline algorithm. And we're still trying to understand what drives that result. And one of the reasons is actually might be that the robustness to the overfitting might not propagate to these post-processing step algorithms. But it's just a hunch that we have, but we haven't theoretically studied that yet. And as I've mentioned earlier, we have much more simulations out there in the paper, have some multivariate design in Monte Carlos, but the more interesting thing that we have an application to non-parametric demand estimation in the context of differentiated goods. So basically, we estimate the inverse demand function that Berry and Hale identify in their paper. But we do not go into functionals that might represent elasticities or divergence ratios or whatever, because it will be much more complicated, and you need actually to control for additional biases that come from the estimation into the functional analysis. So it's a whole different thing to get inference on those guys. But still, in that particular application, we can see substantial gains compared to other algorithms and even the kernel of regression. So the final thing, so for the future work, as I said, we would like to derive the convergence rate and also to explore some ways of boosting the computational performance. Because right now, everything is coded in Python, so sometimes it can be slow. Maybe some tricks like, in XGBoost algorithm can help us, make it more efficient and fast. That's it. So I'm happy to take the questions.
All right, we have time for one question. Are there any? Perfect. Okay. Would the person on Gather please unmute themselves and ask that question? Oh, and would you please step up to the podium and Gather for that?
Could you unmute yourself, please?
And unmute yourself.
Okay.
Go up to the podium and unmute yourself, I believe. Okay, I can just read it. That's fine too. Okay, so in your comparison to deep IV, I assume this is with a fixed neural network architecture. It seems like in practice, a practitioner would use domain knowledge on f of x to design better approximation classes. Any sense on whether that would help the neural network style significantly better, help the neural network style significantly in this case?
So yeah, you're correct. So we just use the default architecture that is in the open source code. We did not tweak that. And as I've mentioned in my talk, yeah, that's one of the reasons why it performs poorly, right? Like the same thing with deep GMM. I think it's just too complex, right? And for this univariate case, you just might want to come up with a simpler architecture for the neural network, and it should perform better. That's kind of my advice, because it does perform well in the multivariate case with this default architecture.
Great. Let's thank the speaker again.
Thank you.